Several buildings face the problem that there is no automatic ventilation installed, nor can it be retrofitted. Due to this, it is very likely that high carbon dioxide and bioeffluents concentrations occur in bad air rooms. In studies, it could be observed that carbon dioxide concentrations starting at around 1,000 parts per million result in a reduction of the cognitive performance. Even physiological symptoms can occur. This leads to a reduced overall well-being in such rooms. Room occupants usually don't notice when the air starts to get bad, since carbon dioxide is not perceivable. Additionally, an adaptation to the air quality occurs so that even bioeffluents are no longer noticed. If rooms are manually aired, the open windows can easily be forgotten. In worst case, this could cause damage to objects inside the room due to strong rain or wind, or if a thief takes the opportunity. In the winter months, this also results in a waste of energy. As a solution, we present a system that enables the room occupants to perceive the air quality unobtrusively. Additionally, it reminds them about open windows. For the system's output, we decided to rely on ambient lights. First of all, I will present the concept of the system to you. At each window and door, we placed ambient lights in form of LED stripes nearby. Since there is just a small distance between them, a relation is recognizable. Additionally, at least one of the LED stripes is usually in the field of vision of the persons in the room. The air quality is determined by the carbon dioxide concentration. To make it visible, it is encoded as the color of the ambient light. In this case, the well-known traffic light colors are applied. If the carbon dioxide concentration is below 1000 ppm, the color is set to green. Between 1000 and 2000 ppm to yellow, and above 2000 ppm to red. The state of the windows is shown by adapting the brightness pattern of the lights. The LED stripes next to the windows indicate the state of the nearby window to make it more visible. If the according window is closed, a constant brightness is used. If the window is open, a fading pattern is applied. The brightness changes continuously from bright to dark. The LED stripe at the door is intended to display the state of all windows in the room. If all windows are closed, it shows a constant brightness. If at least one window is open, the fading effect is used. Ambient lights can easily get obtrusive if the brightness is too high. If it is too dark, it might be too unobtrusive. Thus, we adapt the maximum brightness according to the ambient brightness in the room. If the measured ambient brightness overshoots a specific threshold, the LED's brightness is increased. To save energy, the ambient light is just enabled if motion is detected. After 5 minutes of no motion, it is switched off. The system has been installed in a meeting room which is used by chair members of our university. Usually there are less than 20 persons in the room, and it is used at least once a week. The room has 5 windows and 1 door. The sensors and the Raspberry Pi which controls the whole system are placed on a sideboard. At each door and openable window, a wireless contact sensor and a LED stripe is located. Here you can see an overview of the used sensors and controllers. For our system, we included 2 calibrated NDIR carbon dioxide sensors to compare them. The system is controlled with data of the cheaper sensor, but due to its lower maximum detection range, it can't be used to determine the maximum occurring carbon dioxide concentrations. We included a VOC gas sensor since it can detect bioeffluents. Nevertheless, it was just included for measurement purposes due to its unreliable calibration against fresh air. Additionally, sensors for the room temperature, humidity, air pressure, ambient brightness, motion, and window state are included. Here you can see some of the installed LED stripes. On the left and right, the stripes next to the windows are visible. In the middle, the stripe at the door is shown. Below, you can see one of the stripes with removed cover in detail. Here you can see how the hardware is connected with each other. The Raspberry Pi controls the system, and some sensors are connected to it directly via USB or I2C. An Arduino Mini Pro is used to interface the SCD30 and BMP280 sensors. The system includes a bridge device to receive data of the wireless homematic contact and motion sensors. The LED stripes are controlled by ESP8266 Wi-Fi controllers. For event processing and system control, we used a custom software called Eventerpreter. I will shortly explain some of its features to you. The software is written in Kotlin, which allows the usage of Java libraries. Flow-based programming is used with several reusable nodes. Every node runs in its own thread. The software has a relatively low memory and CPU footprint, which is especially necessary on the Raspberry. To improve the performance of the data processing, we include efficient database data aggregations like moving average. The software uses an independent sensor model and rule engine, allowing combining different data providers. To be able to simplify the development of rules and to test the system, custom web interfaces can be integrated. The software is open source and can be accessed on GitHub. In this overview, the data processing of the system is visible. All external data is at first sent via MQTT to FHEM. FHEM is used since it includes modules allowing to easily interface most of the sensors. Additionally, an integration of the ESP8266 controllers by using the ESP-Easy firmware is directly available. The air control sensor data is gathered by an adapted external program. The SCD30 and BMP280 sensors are read out and preprocessed by the first Eventerpreter pipeline. The second pipeline of Eventerpreter receives all data from FHEM, applies its own sensor model, and stores all data in a PostgreSQL database. The data in the database can be visualized with Grafana. Whenever new data is inserted into the database, generated trigger functions are called, which calculate aggregations and send the results to the third pipeline of Eventerpreter. This processed data is used as the facts of the rules engine. The output of the rules engine are the commands that are required to control the different LED stripes. These commands are sent to FHEM, which sends them to the ESP8266 controllers. Before and after including the ambient lights to the system, we recorded sensor data with it. These data recordings were conducted to get an idea of the carbon dioxide concentrations that occur in this room and to check whether the system is required at all. Additionally, the data was used to compare the sensors, especially the two different carbon dioxide sensors. Furthermore, it should show how stable the system works over longer time durations. The recordings we analyzed for this work were conducted over several months during winter and spring 2018 and 2019. The system is still being used. Here we can see an example of the recorded data. In this case, we selected a day in February 2019, where very bad air quality occurred in the room. At this time, the ambient lights were not yet activated. On the top, the sensor data of the three gas sensors are visible. It can be seen that they are quite similar, especially the two carbon dioxide sensors in blue and orange. This was a quite unusual case where the maximum range of one of the carbon dioxide sensors was exceeded. On the right, I put the air quality rating we used for the ambient light output. We can see that if it had been activated, it would have shown nearly all day orange or red color. The room temperature didn't change much during the day. Only if a window or the door was opened. Their states are visible below. Of course, if a window was opened, the gas concentrations fell too. It can be easily seen that the room occupants didn't air the room enough. Like we saw in the example before, It is required to inform room occupants about bad air quality. Even the maximum range of one carbon dioxide sensor was exceeded. During the data recording, but also later on, the system ran reasonably stable for several months. To get insights on the system from staff members, we conducted a workshop with 5 participants, which included a semi-structured discussion. The workshop took place in the equipped meeting room for 1 hour. The system was demonstrated to the persons in the beginning. In the following, I will present some of the results of the workshop. In general, most participants showed interest in having such a system also in their offices. The meaning of the output of the ambient lights was clear to them. Nevertheless, they also mentioned that showing more and diverse information could be confusing. The participants proposed some additions, but also other use cases were discussed with them. An addition could be to recommend which windows to open and for how long to air the room in the best way. Additionally, notifications on mobile devices were suggested to be reminded to close all windows and to get more information about the air quality. The system could take into account more sensor data to be able to provide a balancing between air quality, room temperature, humidity, and pollen entering the room. Another use case could be to place air quality displays on public transportation so that it is possible to decide which vehicle or route to take. In this work, we presented the design and implementation of an open-source ambient light notification system to inform room occupants. Long-term measurements showed that the air in the room can become very bad, and if the room was aired, the duration was often too short. A workshop showed that people understood the ambient notifications. The participants suggested several additions and use cases. Some of these additions could be added to the system in the future. Additionally, the system could be evaluated in ambient assisted living or private settings to get insights whether the information display should be adapted. Research in the direction of persuasive computing would be possible by evaluating the system's effect on the airing behavior of groups and individuals.